One is heat sound. That's funny. Yeah, try that. 2. Experienced hikers prefer to step over log rather than step on top, then down. Why, Enrico?
Because it's more work to, or therefore their potential energy increases from the top of the log, so they can like come down really hard, coming off the log.
If you got all the energy back, nobody cared. You got all the energy back, nobody cared. You stepped up and then stepped back down, it'd be fine because you keep your momentum going. But whenever you use energy, you're going to waste some in terms of work. And so when you go up higher, that means you're going to waste some energy. Okay, so if you're on a long hike, you don't step on top of the log unless you're 8 years old and want to jump up and down. Because that's what 8-year-olds do. That's also why in mile 8 they're exhausted and can't walk another step.
It's a generalization, sir.
I hiked with an awful lot of 8-year-olds in my time. It's not a generalization.
Walker just feels like an awful lot of 8-year-olds.
Yeah, it was an awful lot of them. An awful lot. An awful lot I carried the last mile. In a little way station to drag them up the hill. You wanted to go on the hike, didn't you? Not bitter. All right, 3. Stephanie, I know the question is here. When a super ball is dropped, may it ever bounce as high as it was dropped from? Why or why not? No. You drop a super ball, it never comes back to your hand. So sad. It's not a super ball, it's a below average ball. It loses energy every time you drop it. Nothing you can do about it. It's going to make heat and sound.
They definitely can.
Really good super balls make very little heat and very little sound. So they bounce quite high, but they never bounce up to your hand. If you throw it down, so he said if you throw it down, it'll get higher. And the answer to that is that's true, because you would be doing what?
Throwing it.
Throwing it, which in energy terms means you're adding more energy somehow. Force times distance while you're throwing it down.
So you added more force.
You added more energy, more work.
But it's higher than where you dropped it.
That's true too. Cheater. All right. 4. Who wants 4? We'll make John do 4 because that's be funny. 4. John, get 3. Yeah, 4 questions twice a 1. Here we go. Suppose you lift the suitcase from the floor of the table. Does work depend on the path you take, straight up or something more complicated?
No.
Doesn't depend on that unless you're counting some sort of frictional. That's true. Does not matter. Time it takes to do it. Does that matter? No. Now listen to me. Energy is extraordinarily useful. Blaze, back row. Energy is extraordinarily useful when you don't have friction. It's also useful when you don't have to worry about time. Okay? When you get done with this chapter, somebody going to ask the question, why did we go through force and acceleration, all that stupid stuff we did? The answer is because energy can't solve how much time it takes to do it. Can't. Energy doesn't care about time, which is a pain in the neck. If it did that, then we'd probably solve problems completely different from start to finish. Okay, but time it can't handle. So, because energy doesn't care about time. Take an hour to get it up on top of the desk, take 10 seconds. Still the same place. Still the same amount of potential energy, correct? Thank you, John. All right, C. The height of the table, does that matter?
Yes.
It absolutely does. D. The mass of the briefcase. Yes, and they said that it affects the weight, right? Good deal. All right, everybody try number 5. 15 minutes. Woo! You guys are doing good today. Everybody's watching nothing. Well, they need the answers to the first part. That's a problem. Back to square one. We have monkey swings from one branch to another branch with 1.3 meters. What's the change of potential energy? Potential energy is equal to mgh, so it would simply be m 4.3, g 9.8. And I'm going to conveniently set his bottom branch at 0, so I can simply go 1.3 for the height. And I put that in my calculator, and I get, what do I get? 54.7 joules. What? 54.8 joules, my bad. She said it right, I said it wrong. All right. Good so far? All right, 5-2. I've kind of explained this, but let's make sure that I'm going to explain this well. By the way, rest of 5, whatever that was, is homework as well. I give you like 7 problems so far, 8 problems, something like that. Let's look at 5.2i. It says cleaning up work. How do I clean up work? We're coming back. Kara, since you were out of the room, let's see if you got it anyways. What's the different paths? When I talk about work, does different paths matter? Kind of okay, but what I really want to start off by saying is no. Because it's force times distance in the same direction, right? So if I'm talking about applying a force in this direction, and I go like this, or I go like this, the force in this, the distance in this direction is going to be the same. So it doesn't matter what weird path I take. The distance is going to be the same. Okay? So generally speaking, different paths does not matter. Now, if I go through a swamp, so my force friction goes up, and I have to do some work for that, I'm wasting useless work.
Or if you go over a
Okay.
mountain and your potential of you have to
That's right. But I'll get potential in your back. That's fine. It's a friction that's the problem.
You don't in real life.
That's the problem.
What if you're like picking up a book
Uh-huh.
and you're trying to get it on a table and you go like this and you like pick it up?
Right. You can do additional useless work if you like.
Okay.
You can. And that's where we got to be careful, because useless work is the bane of all energy, right? Because if I'm making heat and sound, I'm wasting energy. And now I can't use conservation energy because I'm not keeping track of the stuff I wasted, right? If, to jump on top of the table, I jump over there 3 times, jump over here, walk across 3 tables, then jump across here, I wasted a lot of energy. Can't account for that because it's not useful. Okay? So I'll be really careful about measuring my useless work, which I can do sometimes. Force friction, sometimes I can do it. Most of the time, that's going to be a headache. Okay? So we're looking for energy works really, really well when friction is negligible. Okay, that's when you can make really good predictions with it. Doesn't work really well when you got swamps and things going on. Okay? And so as long as the path is independent of friction zone, it works the same. Okay? All right, conserved work. Okay? When you're fighting against a force, that will return the object back to where you started. That is conserved. So if, example 1, I grab a block and I push it against the spring. Okay? Is that conserved or not? It is, because if I'm pushing against the spring, what's the spring going to do when I go? Put it right back. So that's conserved. If I lift the block up, is that conservation force? What's going to happen when I go it? Go back down. So it's a conservative force. If I take a book and I slide it across the table, it gets friction. Conserved or not? It's not going to restore it, right? So conservative forces restore, and that's how I know I've got useful work. So if I'm fighting gravity or springs, or going up an inclined plane, it's going to restore it, so therefore that's conserved, or conservative force. So energy is being conserved, and there'll be no useless work. If you use the word friction, all bets are off. You're going to have non-conservative or useless work. It's not going to restore it. Instead, it's busy heating up the universe or making noise. Alrighty then. Okay, so we're going to leave this up here. Okay. Next time we're going to talk about kinetic energy, which is the third flavor of work. Kinetic energy. Sorry, third flavor of energy. And then we're going to talk about conservative forces. What I'd like you to do for homework is finish those 2 sets of problems. And then I would like you, flip it over, look at the back. I have a block on a stack of books on an inclined plane. I want to know what speed does it hit the ground with. I want you to start to do that problem. Do it for about 15 minutes maximum. And get as far as you can. You probably won't get to the finish line. But you're going to need to check my work. Example number 3 in the back. Okay? I want you to go ahead and do 15 minutes worth of work on it. See how well you do. We'll go ahead and come back, and I'm going to do that problem with you. It would be nice if you had a head start on me. that you guys would be able to figure that out. Yes.
What does it say, like right next to the block?
It says 20 newtons. So somebody's pushing it with 20 newtons per 0.10 meter. It says in the instructions as well. The question itself.
Wait, so Miss Rosie?
Yes.
Can I clarify what we're doing for that?
For homework, you're going to finish.
So.
Okay, good question. You're going to finish 5-1, which you should already have done. You're going to finish 5-4.
I don't think we can finish those.
Yes, you can. You can finish it. But if you can't, you can't. We'll talk about it next time. And then 5-3i. We're going to finish 5-3i. And then you're gonna 5-2i, you're going to look at that one weird problem, see if you can do it on the back.
So wait, counterweights? We're finishing all that?
Yep. And again, where you get stumped, that's fine. But do try it. We're going to put the answer on the board. If you don't get stumped, then you don't know, you don't know. You have a problem with it, it's going to be due on, first week will be due on Friday. Or I give you 0 out of 10 and start your second semester off in Joyland.